Hi guys, this is midterm points back step 8, and it's part D, so you want to have part D in front of you. We're going to do 2 problems, 15 minutes. So, and one of you did get this on the test actually. I'm not sure if you got the whole. No, I think that the person did. It was very impressive because this is a big definition to remember, the definition of continuity. And we haven't been using it in a long time. So we've got this piecewise defined function, and they're asking, is f continuous at x equals 3? Explain why or why not. So I'm just right away going to say this to myself and actually my reader because they want us to explain. So I'm going to start the explanation right now, and it's going to help me formulate what I need to do. So I'll just recall this fact. For f to be continuous at x equals 3, 1, f of 3, or I'll say this, I'll say we need the following 3 things to be true. 1, f of 3 to be defined, Number 2, we need the limit to exist. We need the limit as x approaches 3 to exist. So what we've got to do, guys, is we've got to do the left-hand limit, and it's got to be equal to the right-hand limit, okay? So this is another way of saying, so I'll say i.e. the limit as x approaches 3 of f of x exists. Okay, and then number 3, we need the limit as x approaches 3 of f of x to be equal to f of 3. Okay, so I'm just going to launch right into these things. And then if they're all working, at the end I can say, therefore, f is continuous at that, at x equals 3. All right, so I've said these 3 things. Now, okay, so number 1, f of 3 equals, okay, so I'd be using this top one for plugging in 3. So f of 3 equals radical 4, which is 2. Okay, so defined. Number 2, all right, I need to do the limit as x approaches 3 from the left, and then over here I need the limit as x approaches 3 from the right. Okay, so I've got to find both of these. And I think notation is important here, guys. Okay, but below it, I'm going to use this kind of easier notation. So I'll go as x approaches 3 from the left, y approaches. So 3 from the left, I'd be using the top function, so y would be approaching 2. And then over here, as x approaches, okay, I'm just doing some work below. As x approaches 3 from the right, y is approaching, I'm using the bottom function, also 2. Okay, so back up here, I've got this equal to 2, which is equal to that. Okay, so they are in fact equal, so the limit exists. And then step 3, since both of these are 2, I can say the limit as x approaches 3 of f of x equals f of 3. Check. Okay, so these 3 things happen, and then I'll just say, therefore, f is continuous at x equals 3. Okay, because those 3 things checked out. Okay. Now, actually, I pulled this from a more complicated problem, and I only gave you, like, the first part of it. So we'll do the actual problem at some point, but see, this was the actual, no it wasn't, this was it. This was the actual problem right there. So see, there's parts B and C also that look really interesting, so we'll do those at some point. So we only did part A, it was 2 points, part A, and so it looks like you didn't really have to be at like, because this equals that equals 2, therefore, okay, I don't know. So they have this. This seems weirdly not thorough to me. Maybe it is, I don't know. So then over here, what they'd be looking for was, you say yes, and you equate the values of the left and right hand limits, and then you have an explanation involving limits. Okay, so they want those. That's what they're looking for. Okay, so you had to say yes and at least equate the left and right hand limits for 1 point here. Okay, and the explanation tying all 3 of the conditions together would have been good. Okay, so now we're going to do this one. Okay, so let f be a function defined, and these were no calculator ones, by the way. Let f be a function defined on this closed interval with f of 0 equals 3. The graph of f prime, the derivative of f, consists of one line segment in a semicircle as shown above. This is f prime. This is not f. Derivative graphs, Susan's table, that's what we're dealing with right here. It really is everywhere, that topic. On what intervals, if any, is f increasing? Justify your answer. So let me write down what I would need to have. I'll say f is increasing for values where f prime is greater than 0. Okay. And then I'll say whatever. Okay, so I'm being like super thorough. So f is increasing on, we're looking for where f prime is positive. F prime is positive. This is f prime. It's positive where it's above the x-axis, so right there. Okay, so it's increasing on, okay, -3 to -2. Okay, -3 is a positive number, so I'm including it, and then it's 0 there. They actually included this, though, which had bothered me. And so I should probably find out if it really should be included. I'm like positive that you could go either way. It makes more sense to me not to include it because 0 is not a positive number. Okay, so anyway, I'm not going to include it. All right, so f is increasing on this interval because this is where f prime is positive. Okay, and you could probably get away with less words. Okay, I'm just being super thorough. Okay, B. Find the x-coordinate of each point of inflection of the graph of f on this open interval. Justify your answer. Okay, so I need to know that a point of inflection of f, and then I'll say occurs at the extremas, at the local extremas. Okay, this might be like, the way I'm trying to do this, guys, is not necessarily the way I would do it on my own, but I'm trying to like help you develop a strategy, and I think a good strategy would be recalling any facts. Okay, so I'm recalling the facts, then I'm thinking about it, because that also, it takes care of two things. It helps you figure the problem out, but then it also helps you set up your explanation, like a nice strong explanation. So I'm recalling this fact. A point of inflection, you should write this out. Point of inflection, that's what should go right there. A point of inflection of f occurs at the local extremas, or extrema, of f prime. And I'm going to be like pretty circular here, but I just want to be super sure that I get these points. At the extremis of f prime, so at x equals 0 and x equals 2, f has points of inflection because this is where, these are where, ugh, sorry, these are where f prime has extrema. Yeah, I think extrema is the plural. Okay, so let's look here. The function is increasing on this interval since that. Guys, I'm sure that would have been enough, okay? But, you know, obviously that's what they wrote. But I think, even though this is a bit loquacious, I think better to err on the side of caution and have a good, strong explanation. Okay, so, and that is the first time I've ever used the word loquacious. All right, so they needed the interval and the reason. All right, 2 points. Alrighty, so, oh, duh, I didn't even go over the A. Okay, so that was A. B would have been this, so take a look at that. We get 1 point for just stating the x-coordinates and another point for the justification. And now I really like this last one. Okay, so part C, find an equation for the line tangent to the graph of f at this point. Okay, so, I'm going to need to use the point slope formula. So I need the point of inflection. This is a tangent line, so the point of tangency, I mean. I need the point of tangency, and I need f prime because that's going to give me the slope. Okay, I need f prime at that point. They're telling me that they want this tangent line at this point, and then I just need the derivative. So I need the derivative at 0. Well, this is the derivative graph. And its output at 0 is -2. Okay, equals -2, so m equals, the slope is going to be equal to -2. Y minus 3 equals m x minus 0. And you can stop there. So, but here, all right, they have this, and they solve for y, but you just get 1 point for that one. Okay, guys, I hope that this is helpful, and I will see you soon. Bye-bye.